Bob, please say who your question is directed to first.
Yeah, well, this is to Albert, but also it had worked for SCE too. In trying to work out what the hazard and the risk are, you can't ignore aftershocks, and everybody knows that. But my question for Albert was just simply, in what way is that accounted for in their program?
Okay. Is this on? You guys hearing this? Yeah, there we go. So at the moment, it's not. And that's a shortcoming that we've realized, and it's not because it's complicated. So first of all, when we do hazard, we assume it's Poisson. So that means, as you know, it's memoryless. And so it's really complicated to introduce aftershocks which depend on a main shock event into that process. So that's an area of active research, is to move beyond a Poisson process when we do hazard. And so we've been working on that for a couple of years. It's going to need more time before it's ready, but we recognize it's a shortcoming. The other thing to think about with aftershocks is when we think about a main shock event, it's going to happen and we're going to have no idea it's there. It's going to be, so when we think about a risk, we look at populations in buildings and we think about what those populations are going to be at a given time, and all of that assumes that an earthquake is just going to happen. After we have that main shock, we're going to start having decisions being made, and if a building is not occupied, or if a building is damaged during that main shock, we may not let people occupy it. And so now we have human factors starting to control that risk and starting to feed back. So it's not like we can just put aftershocks in without accounting for decisions that could be made after a main shock event to accommodate the risk. So the other challenge is after you have a main shock event, you need decision making to think about, when do you start repairing things? Should we let earthquakes happen before we get out in the field and do repairs? And I think there's a lot of questions about how we respond to events and how we accommodate responding to an earthquake, given the fact that aftershocks are going to occur. That needs to happen. The other thing that I think is very interesting about aftershocks is, from not just PG&E's perspective, but the larger perspective of a population, is what does it mean from a psychological perspective? How do we deal with PTSD and stress with people that might have lost their homes, or people that they know, and now they have constant reminders from these aftershocks, and what does that mean? And from a mental health question, I think that's something else. That's not a PG&E question, but it's a question that I think about. So I don't know if you have a follow-up, Ken, or.
If I could, I could add to that a little. So yesterday we had the Structural Engineers Association led a day-long seminar to commemorate the 30th anniversary of the Northridge earthquake. There has been more discussion about those real-world human factors and the decision-making. This was the focal point of Lucy Jones's keynote presentation yesterday. I think this is an area where probably all of us can benefit from learning from the social scientists about how people make decisions and so forth. I think it was an insightful talk. And PTSD, I think, one of the things we all saw on social media yesterday as people were reflecting on the Northridge earthquake is that a huge number of people were, affected by post-traumatic stress as a result of that earthquake. And this should be expected from future urban earthquakes in California as a major factor. I don't know what else to say except, other things that have been identified are the number of people that would be needing to, displaced from their homes and find safe shelter somewhere. And so there are some real challenges there. This is something that we came across and Wine and others worked, and Lori Johnson worked on for the Haywired scenario. And I know that's much of the focus of your workshop there is the recent simulations for Bay Area earthquakes. And, it's not specific to the Bay Area, but it's also an issue down here. It's just been studied better up there as a result of the teamwork on the Haywired scenario. That's all.
I think there's one right before you, and then we'll come to you. You want to go ahead?
I can go. Sure. This is a let me first ask a question to Albert, and then maybe I ask the second question to Ken. The questions I have for Albert are like clarification questions so that I better understand what you presented. When you're modeling the damages, you're doing it with one map at a time, and then each map has spatial correlations, albeit they're not necessarily region-specific, they're spatially correlated in another way, but one map at a time, so that every time you're assessing the network level damage, it's done through spatially correlated motions. Is that it?
That's correct.
And then the second question is, when you're computing the damage, or rather the losses, is it like linear in that you have one building damaged and it's like $10, two buildings damaged, it's $20, or is it more than $20?
So if we would have done them independently, we would have done that. We've calculated $20, right? But now when it comes to the risk amount, we have to take that $20 and we have to multiply it by a nonlinear factor. And so it might actually come out to be $20.2, right? So $10 might stay at $10, $20 might start at $20. But now if we had 10 buildings that were damaged and it's not $100, now it might be $150.
And that data to compound to accelerate those losses, how do you decide that? Where does that come from? Is it something data-driven model, or is it another simulation of?
That's a decision. It's how, so we have a whole enterprise risk group that works on defining that function. And that function is, we do a lot of self-insurance, and it gets to a point beyond that we go to insurance, and so some of that decisions are at play. But it also, outside of PG&E, there is probably also a similar scaling factor that is just inherent into humanity, I think, too. And so big events are just harder to deal with. And that's why we have insurance, and insurance typically is, it's for catastrophic loss, it's not for day-to-day loss. So that scaling factor, I can't tell you what exactly it is, I think for proprietary reasons, but I also, it's a decision making, and so, we have that on a society level in some way, and what it is hard to define.
Thank you. And then the second question, let me just first direct it to Ken, but I guess, you'll have answers too, but for, entities like Southern California Edison, PG&E, when your things break, there's a loss there at that time of the event. And then, of course, there's the recovery period. And then the more you remain not functional, the more money you're losing. So does that, get into your calculations? Do you take into account that recovery period where you're still losing money, you're still incurring losses? Is that part of the workflow already? That was a question to Ken, I guess, but it's a question to the energy suppliers in total.
I wasn't able to hear the question very well. Sorry about that.
Okay, so to try to answer that, E.T. So the question, Ken, I don't know if you can hear me better, was that
Yeah.
how do we account for downtime in our loss estimate, essentially? And so when we think about downtime, we project out, given how many customers are out of power, how long it's going to take to recover from that. In that, so we have that metric there, but we're also, if we can't deliver power, we are losing money, but I think we're also penalized for not being able to deliver power, because that's like a mandate that we are delivering power. So we do factor that in, and that's an important thing. But one thing that's really hard is, when we have winter storms coming in, we might look to bring external groups in to help recover faster. But when there's an earthquake, we have no ability to forecast that damage is coming. And so one thing Ken and I have been talking about is how do we at least start using the same language in terms of, this was for aftershocks and how we respond to aftershocks, but making sure that when we come in and respond to earthquakes that we're using the same language and we're talking about the same types of damage and things like that, so we can recover faster given the fact that we have no startup time. like we would for bigger events that like storms. So like in the south, hurricanes, they know hurricanes are coming, they get ready so that as soon as the hurricane is over, they can start repairs. And they already have a huge force coming in and being ready to assist.
Yeah, so this is Rob Graves, and I just want to make a quick comment regarding aftershocks. That's a very important concept. So the term aftershock is arbitrary. Aftershocks can be bigger than the main shock, in which case the first one is the foreshock, and then the aftershock becomes the main shock. And an example is the 2019 Ridgecrest sequence, right? We had a 6.4, then 30 hours later, 7.1. It is very it's a complex process to try to assess what the kind of cumulative effects there are. Ken kind of referred to the scenario that they're going to be considering this year, and that actually, it's a doublet, or call it a doublet, but it's basically, you could think of it as two earthquakes, separate earthquakes that occur close in time. Could be main shock, aftershock. So, it's not a problem, or I would say it's a very difficult problem, but it's not one that's being completely ignored by the utilities.
But when we don't look at probabilities of doublets when we think about hazard, right? And our ground motion, I think, would go up from a hazard perspective if we would consider these types of triggered events.
Correct. Although the statistical models in terms of probabilities are getting better,
Yeah.
and there is certainly a very, a time dependent. So an earthquake happens, the chances of having another large earthquake immediately after that are actually fairly high, relatively speaking. A week later, they're much lower, and so forth. But you're right, the probabilities, trying to factor that in becomes a very complicated problem.
Thank you. I have a comment question on the issues related to spatial correlation. In the presentation, you pointed out very well the importance of incorporating spatial correlation and intensity correlation when doing risk estimates to spatially distributed portfolios of assets, infrastructure systems. The studies show the spatial correlation is really region dependent, and in some cases also really scenario dependent, while the available models that are calibrated on a few data are typically ergodic, so they are very simplified. So the standard practice considers spatial correlation model in addition to the empirical correlation model, to the empirical ground motion model that are somehow oversimplified. And so I was wondering about your view on that, about the sensitivity studies on different spatial correlation model on risk estimates, and the possibility also to use simulated ground shaking scenarios as they are, and of course they incorporate naturally a spatially correlated that is physically sound, or also to use simulation to inform spatial correlation models in a more physical way.
So, yeah, and that was really the, when we think about, I think the roughness of the models, where we're getting high and low patches is probably about right. So right now, what I just sort of described is a plan, and we are most of the way through that. So we have to get there first, and then we can start figuring out how to improve it. But what you've described in using simulations to develop region-specific correlation models, well, actually, if we go through and do a good job developing non-ergodic models, we should capture all those spatial effects. And so that's really the vision, is using simulations to get to spatially varying ground motion models that capture those effects and that repeatability. And so that at the end, the spatial correlation is there is no correlation. So that's, and to get there, we're going to have to use simulations because we don't have, we can't get that from small magnitude data. We can't see how the large magnitudes are going to be spatially correlated. So that's going to be a really important stage. And yeah, we can do that from we can develop those scenarios from non-ergodic ground motion models. But we could also do that, and I tried to outline this through on the last couple slides, is instead of using non-ergodic ground motion models, we could use numerical simulations to generate those scenarios. And then look at and use those simulations, but downsample them and make sure they're consistent with the hazard that we expect for the region. Because I think that's one thing that's lacking is right now, scenarios are treated as a deterministic event. Here's a magnitude 7 on the Hayward event or Hayward fault or some other fault, and we're going to grab a maybe 50 or 10 or 15, whatever number of samples from that. But that's only one event, and the actual hazard in the area is a whole suite of different magnitudes and a lot of different sources. So let's look at those all when we think about the response. Thank you for the question.